I'm happy to come here again and again. Okay, this is a joint work with Don Stanley, and we started this work in the beginning of 2013, so when I left Korea. So we started 2 projects, and we finished 1 project this last year summer, because I didn't know anything about the rational cohomology or rational homotopy theory. But the question was, it came to my mind from the paper of Professor Masuda and Hattori and Panov. So they discussed, their title was so nice, you know. So cohomology ring, rings of manifolds. So then I thought, okay, all cohomology rings are known for torus manifolds, so I don't need to do anything. Then I tried to understand what is done and what is not done. Then then I realized, okay, if the manifold is little complicated, then it is little bit difficult. So I started to find out what do you mean by the complicacy. So they have nice description, of course, for equivariant cohomology. But if we take some manifold, so by torus manifold we mean even dimensional closed manifold which has effective torus action with non-empty fixed point. So that means at least it has one fixed point. But still it was complicated to me. So then I decided, okay, let's try to make it less complicated. Then we know that since we are toric topologists, so I'm not going to say the details. So we know that what do you mean by a standard representation. So what we can consider, let's take a point from this 2n-dimensional manifold, and if we impose that X has a neighborhood which looks like a open subset of the standard representation for Cn. Okay, so this is equivariantly homeomorphic. Then what can happen? We know that they also discuss something can happen. So what in their paper is there? So you can consider this quotient space or orbit space. So this will be nice manifold with corner. So this is homeomorphic to and suppose we can give a name. So I will say that P means polytope, but it may not be polytope here, some other little crazy things. But now the question will come whether we can construct the 2n-dimensional manifold using the Davis-Januszki's construction. So sometimes it is easy, sometimes it is not. And they have the formula that if the polytope it has second cohomology is 0, then we can use that construction. Otherwise we cannot. And okay, so what should be the example which are torus manifold but not toric manifold? Toric manifold was discussed by Davis and Januszky. Almost, I think everybody here it knows. So they gave toric manifold, and then I think Professor Hattori and Masuda, and again several people, but I can just remember 2 names. Let's give some examples which are not toric. So this is important. So we know easiest manifold in our life, which is n-dimensional sphere. So this will write Z1 to Zn and then X. belongs to Cn cross R, which should satisfy this condition. So Zi square 1 to n plus x square equal to 1. So this is a nice manifold, okay, smooth manifold, and we have some torus. So we can just say that, okay, T1 we take Tn, which belongs to compact abelian torus in Cn. Okay, it does not make sense, but we can impose mod of Ti equal to 1. Let's define the natural action. Maybe almost all of us we know, but let me recall this one. So Z1 to this is just multiplication by component wise. So Tn Zn x. Okay, now somebody can ask, okay, what should be the, whether it is a locally standard action or not. That means whether it satisfies this condition or not. But that is easy to check because we have north pole and south pole. Here north pole will be just 0, 0, 0. Here is negative 1 and south pole is like positive 1. And then if we just forget one of them, we can see the remaining will be exactly some. There will be homeomorphism from that set to Cn. That is just by given by what projection, which is stereographic projection. Okay. So let's ask the question, what will happen S2n mod 10? So that means the orbit space, how it should look like. So since the action is just component wise, it will be just x1 to xn x. Now it should come from Rn cross R, but which we can say that, okay, Rn plus 1, and it should satisfy the similar condition. So that means xi square plus x square equal to 1, I equal to 1 to n. Now if we try to draw some example, okay, I will fix this notation. So this will say Qn for the lecture. So, okay, what will be Q1? So this is in dimension 2, so that is very easy. So this is x1 direction, this is x direction. So only this line, this will be just Q1. So this is Q1. Okay, now if we try to see what is Q2, this is, x1, this is x2, this is in direction x. Okay, let's try to draw. So this is 0, 0, negative 1, 0, 0, 1, and here is 1, 0, 0, here is 0, 1, 0. So this is not exactly simple polytope, but it has a nice structure. So you can define the faces of, so can define faces of Qn. Okay, now what we have? We have S2n, that is 2n dimensional manifold, and we have Mn, two types of manifold. But Mn we don't know how it looks like. But
isn't that Rn plus? Isn't that Rn plus crossover? Isn't that Rn plus crossover?
Oh, thank you. Yes. This should be either, okay, we could say this is positive or this one. Okay, thank you. That is good. Okay, so we have two objects, Mn here, but Mn we don't know what is that, so we cannot handle it. At least S2n we know how it looks like, so let's try to play with that. So what we want to do? We know surgery. So we'll try to take a point from Sn. So what type of point? We'll take any point, and then it has a group action, so we can consider the orbit of that point. So let's take a point x belongs to S2n. So that means we know this orbit. So okay, this looks like isotropy, but it is not isotropy. So this is orbit of x. So since it is a smooth manifold, what we can do by slice theorem, we can construct a tubular neighborhood of that orbit, and which will look like a normal bundle of that orbit, and delete that normal bundle of that orbit and take two copies of the similar things and glue them by identity map. So what we will get? We will get some other manifold, which we can say, so we had Sn and we deleted a normal neighborhood of this Tnx. Okay. So what we did, we need to take the closure. Now we have to identify. So we have two copies of this. So Tn normal neighborhood of Tnx. Okay. To distinguish this, we can just say x1 and x2, but these are similar, same copy. x1 equal to same. So if we identify via that boundary of that neighborhood by identity map, we will get some new manifold. So which we can say this is the connected sum of this. So by definition, this is, we can say, S2n connected sum S2n, but along an orbit. So and that orbit dimension we can say Tk. So if this is homeomorphic to Tk, we can say along Tk. Right? Okay, now let's try to see how that manifold should look like, whether it is a toric manifold or not toric manifold. So let's take example n equal to 2. So we have S4 and we have S4 here. So S4 has the orbit space which looks like this, and this has orbit space which looks like this. Now if we take a point x1 here, and okay, this is bad notation, but x1 bar and x2 bar. So x1 bar will look like x1, x2, x. This will look like x1 prime, x2 prime, okay, x prime. So what we will assume, both of them non-zero. So that means this point will have image under the orbit map. Okay, let's take the orbit map. Pi S2n goes to Qn orbit map. And since it is like equivariant, we can make it equivariant gluing. So equivariant gluing. So this will say that S2n connected sum Tk S2n is a torus manifold. So that has very nice structure. Okay, if we try to do that gluing along T2, so that means the orbit space will be, we are deleting this point and gluing this to orbit space. So okay, how it will go, I'll make it little better, and it is like this. So topologically it will be this space and we are deleting the inside. So what we get again nice manifold with corner, but the orbit space is not simply connected. So that means it is not contractible. And the previous result, I think Professor Masuda and his collaborator, they did found the cohomology ring when the orbit space is contractible. So in 2000, up to 2014, I knew that result. Then when I wrote this paper and uploaded to archive. Then Anton had an objection. He said, no, we generalized that result a little bit, and their generalization was that if the proper faces are acyclic, so that means the homology groups are 0, it does not matter whether the total, the orbit space, bigger space, is contractible or not, but if the proper faces they are contractible, then they have some result. But beyond that, they don't have. Then I realized, okay, we have much more examples. So what we can do, so let's take 3-dimensional nice manifold with corner. So it will look like this. Okay, and we have, so this is topologically suspension over triangle. So take another copy. Now if we take a point from this face, so this has 3 facets, F1, F2, and in the back side F3, and this is F1 prime, F2 prime, in the back side this is F3 prime. Okay, we'll take point here and take point here and try to glue them. So what we mean that not only the connected sum, not only we can do for manifold, we can do for manifold with corner also. And it can be like, it can be done very nicely or smoothly, so that it is again a nice manifold with corner. But now what we can see, it will have a face which is coming from F2 and F1 prime, which is not contractible because it looks like hollow. So this will give some example which the previous authors didn't include. So let's work with that, how we can do. So what is the important object here? This S2n action, this torus manifold. Okay, why it is important? Now I will tell that. Most of the time what object we are interested in? Toric manifolds. But now using the similar discussion, what we can do? We can do the equivariant connected sum of toric manifolds. And that equivariant connected sum will produce as many as we want torus manifold which are not toric manifold. And many cases the orbit space will not satisfy the previous condition. Like orbit space may not be contractible, and there may be some faces, proper faces which are not contractible. So what can we say about their cohomology ring? So that is natural question. Now how we can handle it? So we know this one and we know toric manifold. So the next nice object should be connected sum of toric manifold. So let M and N2N, okay, be toric manifold. So then we can say M2N connected sum. We have to be little careful when we are taking equivariant connected sum, but it can be done. And I think it is known for a long time, but in paper of Carlson and Grusberg or somebody, they discussed explicitly, and also many other toric topologists. So then this is a torus manifold. But now how it looks like, we don't know topologically. But what we can do, suppose we know the orbit space here. So this looks like P1n, and here is P2n. And we are taking the connected sum along some face, F1 here. So this is a face. Okay, it can be total also, and this is F2. It can be the P2 also. So if we take a point here, P1 belongs here, P2 belongs here. See, this connected sum we will give the corresponding connected sum here. Okay. So in pictorially, let's try to do here. Okay, and something is here. So we are trying to delete some point and some point here. But if we observe this one, this was the observation of dawn. So how we can write this one? We can consider this point and consider this vertex. So this vertex has a neighborhood which looks like Rn positive and contains this vertex. So this one is equivalent to say that, okay, this line, and let's go a little bit this way, and I will put dot and here. So you can make the point P1 here, P1 here, and this is the vertex V1. This is vertex V1. Here also we can take this is vertex V2 and make it like this and try to shrink it. I will say why we are trying to shrink. So this is still topology same as this, and this object has no difference up to diffeomorphism still. But what it contains P2 and this is V2. So what this picture is suggesting, that we can write this toric manifold as a connected sum of S2n as well as Mn. Okay. See, this is after, okay.
With orientation.
See,
Don't you have to be careful with orientation?
Yes, of course we have to be careful about the orientation. So always whatever map we are taking, orientation preserving. It preserved because it has a orientation class. So whenever we will take the connected sum, it should match. But how we are writing? So topologically what will happen? This picture will say that, okay, that M2n, it is homeomorphic, not equivariantly. Okay, homeomorphic to M2n, which we agree is 2n. That is true because the neighborhood of this vertex exactly looks like Rn positive. So the inverse image will look like Cn, and the Cn just we are taking, deleting one fixed point of S2n, so which is Cn. So you can do that. Now what we are doing, here is equivariant connected sum, Tk. So here was normal connected sum, here is, n to n, normal connected sum, S to n. So this will be homeomorphic to m to n connected sum n to n, and then connected sum S to n. Here is equivariant. So what we can do, we can shift the equivariant connected sum in the torus part. Okay. So that is, yeah, Don observed that one, so it was good. So you can shift that. Now we know what is the cohomology ring for this toric manifold. So we just need to know what should be the cohomology ring for the S2n connected sum S2n. But S2n is easy to handle. We know why it is easy to handle. Okay, let's do it. I will not delete this one because we are going to use it. And now Don and his collaborator Pascal Lambretz, they had a result regarding the what should be the Sullivan model for the Poincare diagram. So what do you mean by that? I mean for the complement of some set. Okay. So what does it mean? So if we have something, A is an inclusion to X, and if we know the model for this, if one knows, okay, knows model means Sullivan model for, okay, star, then what can we say? About the model of x minus a. So that means what are the things we know? We know model of a, we know model of x, and we know how this map is induced between the model of x to model of a. Then can we say what should be the model of this complement? So that's this problem, I think, is known as point care embedding problem. And they could not solve all, but they did various conditions, which includes many. So what we had, that Tk, right? So Tk is a, so that means it is a k-dimensional object. Where it belongs? S to n. And we know the model of k-dimensional torus. We know model of S to n. Now whether we can say what should be the model of the complement, that we wanted to know, right? When we defined that connected sum of S to n and S to n, then we know that how we defined, we deleted n normal neighborhood, right? Nice normal neighborhood of the orbit, and we glued them together. So what does it mean? So this diagram can induce that, okay, we have this Tk, it goes to normal of Tk, which sits inside S to n, and we have this map. So this map is just like collapsing along the fiber. Okay. So that implies this gives our S to n connected sum. I'm rewriting again, but it is good. So this is S to n minus n Tk bar connected sum. Okay, now we cannot say this is Tk, but homeomorphic to this Tn minus n Tk. Okay, so it is enough to know what should be the cohomology or any model for this complement. Okay, before that, maybe we'll discuss some other things. How is my cell phone? So the second thing is, so what we used this one heavily to say what should be the model for this. So now let's define, okay, what should be that definition? I think I don't have that. But if you have any question, please ask. Let's L and K. L n is fixed now. 0 equal to faces of Qn. We said what is the Qn. We know that definition. Now for K belongs to 1 to n, we are trying to define another set, new set, which we say L, n, okay, we can put third bracket or just n, K, this is equal to L, n, 0. So you want to forget some of the faces. What are the faces? They are, okay, F belongs to L, n, 0, such that F contains, I will say what is Ek to En, contains edges. So since En is there, Ei's are edges, so where E1 to En are edges of Qn. So we fixed a numbering like here. So this is like E1, this is E2, this is E3. So that we can define. So we are trying to define the subset of this one, not the subset, but subset of the faces of this. So using this, we can define V and K. This is a subset of now this polytope, not polytope, manifold with corner. So this is union of F, where F belongs to this L and K. It looks like little bit complicated, but not complicated. It is not the complement of the faces which contains E1, E2, En, but this is union of all faces which has, okay, sometimes may be intersection, sometimes may not, but does not matter. Now we know the orbit map, so we can define U and K, equal to pi inverse of V and K. So this is an object. Now if we try to see example, so suppose here we take F. F is this face, or K. K is one dimensional. So example we want to give, suppose n equal to 3 and K equal to 2, then what will be V and K? So V 3 2, it will look like, so all the faces, what are the faces we deleted, which contains these two edges. So that means this will be look like this one. The picture will be little crazy, but I will try to make it okay. So this side and this side. So these two wings remains, and other, including the interior and this face, it is deleted. And now if we try to take the inverse image of this one, so we can define the inverse image of this one, so that will belongs to, so pi inverse of this object V and K, V and K, that is a subset of S2 into 3, so that is S6. And now how this object looks like. So this is inverse image of this will be the push out of this diagram. Okay, I should write other side. Okay. So inverse image of this one will be just S2, right? So S2, which is a subset of S6. So this is a subset of S6. And this is inside another S4, which is a subset of not equal to S6. So it has another inclusion in other face, which is again a subset of S4. Right? So the inverse image of this one is nothing but push out of, okay, what is this one? You said name U3 2. Okay, agree? Now what is this map? It is an inclusion, but the dimension of this sphere is higher than the dimension of this sphere. So this map is null homotopic. So this F and G, these two are null homotopic. So the push out will be homeomorphic to, or homotopic to S4 with S4 with S3. What is S3? Okay, I should say cone of S2 attached to it. So here is one cone, here is S2, and here is another cone, C S2. But this is nothing but S4. S3. So this is S4 with S3. Okay, so this is homotopic to this. So what we can do, now we can break it, the S2N or the complement. So using this argument, what we can do, we can show that this is homotopic to the wedge of a sphere, lower dimensional sphere. So this is just an example, but for other cases also we can do. That needs a proof and little non-trivial. So that that gives our lemma. So that we will say that U n k, this is homotopic to wedge of, okay, I will say I equal to 1 to t, then wedge of ti, I will say what is this t, 2n minus t plus t equal to, yes, 1, where, so this is lemma, where t equal to n plus 1 minus t, and I goes to 1 to t, and k is equal to 1 to n. So that gives our result. That is the main result, and then we can say what should be the homology group or cohomology group of that wedge very easily, and we can say what should be the model also. So that means that is homotopic to this one. So this object is homotopic to this one because this is made from something which looks like
pi inverse.
Huh? No, U. This is U. Huh. So U, so we don't need pi inverse. So now we know what should be the model of this one and what should be the model of this one. Now we just need to say that how we can define this model. But for the model, what we need, even if we know the model for this, we cannot say what should be the model for the connected sum. So at least we need to make it, one of them is free minimal model, something like that. Okay, freely generated minimal model we need. So for that we have to do some calculation, and I'm happy that Don helped me. I didn't know that how to do that minimal computation of minimal model. So do you have any question? But this is the important thing. The first important thing was, if we take the connected sum, equivariant connected sum of two toric manifold, that is homeomorphic to connected sum of two same toric manifold and connected sum of this even dimensional sphere. Now we can compute what should be the model for this. Okay, I mean complement of this one. And do I have time? I can just say how we can do that. Okay, I don't have. But is the idea okay? So maybe I will stop here. Thank you for your attention.